to be reviewing free body diagrams, when to use them, and we're going to go over some scenarios when you would use them in a problem.
Free body diagrams are used to illustrate the relative magnitude and direction of forces on an object. Usually, an object is represented by a box and the forces by arrows in the direction in which the force is acting on the object. In free body diagrams, it's important that arrows are representative of the magnitude of forces and that all forces are labeled. In the context of a box resting on a table, the free body diagram of the box would show a downward force of gravity and the equal and opposite upward normal force.
First, we're going to show you the dreaded elevator problem. In this problem, we have Carolyn sitting on Elizabeth in an elevator that's not moving. The downward forces acting on Elizabeth would be her force of gravity equal to her mass times the acceleration due to gravity of 9.8 meters per second, and Carolyn's force of gravity equal to Carolyn's mass times the acceleration of gravity. Because they are at rest, the force acting upwards must be equal to the downward force. Therefore, the normal force of the floor on Elizabeth is equal to the sum of the forces of gravity. There are no horizontal forces acting on the system. Now assume the elevator is accelerating upwards. Because the acceleration of the elevator counteracts the acceleration due to gravity, the force up must be greater than the force down. Therefore, the normal force must be greater than the force of gravity.
Now into the next problem. Here we have Carolyn standing on a raft in a pool. Because Carolyn is at rest, when looking at the forces acting on her, the downward force must equal the upward force. So we can see that the downward force of gravity acting on Carolyn must equal the magnitude opposite direction of the normal force of the kayak on Carolyn. Now if we look at the kayak, we can see that it's also at rest. It's not sinking or floating in the air. Therefore, the force down must also equal the force up. So the downward force of gravity acting on the kayak must equal the upward buoyant force of the water pushing the kayak up. If we assume there is no wind in the system, then there are no horizontal forces acting on it.
So now we're going to assume that there is no air resistance, but there is water resistance. So if Carolyn stands at one end of the kayak and walks towards the other, we see that the same forces of gravity and normal force are acting on Carolyn and on the kayak. As you can see, the free body diagram of Carolyn is on the right with its forces represented in pink arrows, and the free body diagram of the kayak is on the left with its forces in purple. So the forces of gravity and normal force are the same because Carolyn's mass and the kayak's mass have not changed, and the acceleration due to gravity is always 9.8 meters per second squared on Earth. However, the system now has horizontal forces acting on it. So when Carolyn walks across, her foot applies a horizontal force backwards on the kayak. Now because there is friction between her feet and the kayak applies a positive horizontal frictional force forward on Carolyn. Now if we look closer at the forces acting on the kayak, we see that the water resists the movement of the kayak backwards. So we can kind of think of this as the friction between the water and the kayak. However, because the net movement of the kayak is negative, so the kayak moves backwards, this means that the force that pushes the kayak backwards, or the force that Carolyn's foot applies to the kayak, must be greater than the force of the water resistance on the kayak.
Now into the next problem, inclines. In free body diagrams, we don't draw forces at angles. Instead, we shift the y and x axes to match the angle of the incline. So as the object, which is me and the skateboard combined, roll down a hill, the only forces acting on the object are my normal force, force of gravity, and the frictional force, as this free body diagram shows, which has been enlarged for better understanding. Since it is gravity pushing me down the hill, we have to find the x component of the force of gravity. We do this by taking the sine theta of the mass times acceleration of gravity to find the force going in the right direction. Theta is found in the angle of the incline. Then we find the y downwards component acting on me by taking the cosine theta of the force of gravity. The y upwards component of the system is normal force, which is always perpendicular to the plane and opposite to the y component of gravity. So it is equal to the cosine of my force of gravity as well. Because the wheels of the skateboard are rolling and not slipping, there is a force of static friction acting up the hill.
How you feeling? Oh.
In the arms of the angel.
Alright guys, like and subscribe for more.